All right, so hello everyone. So welcome to today's talk, and we are very happy to have Andy Neitzke from Yale University for today's talk. So Andy got his PhD in 2005 from Harvard, and after that he did postdocs at the Institute for Advanced Studies and Harvard, after which he started his faculty position at UT Austin, and now, as of 2020, he's a professor at Yale, and he is one of the pioneers of the wall-crossing phenomena in supersymmetric field theories, and today he will talk about exact WKB abelianization in supersymmetric field theories. And before I would like to mention that this talk is being recorded, so if you don't want to be seen, turn off your cameras, please. And also, if you don't want the live transcripts as the subtitles, you can turn it off. And with that, Andy, the floor is yours.
Great. Thank you very much for the invitation and to speak and for the introduction. It's really a pleasure to have the opportunity to talk about exact WKB in front of this particular audience. On the other hand, it's also incredibly intimidating because you all are the real experts on exact WKB. I came to the subject kind of indirectly. So it's my hope that at least someone will learn something from this talk, either me or you, or maybe both. Okay, so what's the aim of this talk? So I have two aims. So one is just to present a particular point of view on exact WKB, which kind of came out of thinking about it in supersymmetric quantum field theory. And in this way of thinking, in this kind of geometric way of thinking, the most important feature in exact WKB is that it's a kind of abelianization. So the key thing to have in mind is the process of taking a matrix and replacing it with a diagonal matrix just by diagonalizing it. The idea is the exact WKB, the essential process that's going on in exact WKB is some high-powered version of that fibered over a Riemann surface. So I want to describe that picture, which I think involves ingredients that'll be familiar to many of you, but maybe it's a slightly different way of thinking about it. And then the second thing I want to do, time permitting, is to talk a little bit about one aspect of the story, which is the Stokes automorphisms. I'll remind you what these are, but these kind of canonical transformations that appear in the exact WKB theory, which have an interesting interpretation in either in supersymmetric quantum field theory or in Donaldson-Thomas theory. Yeah, so I want to explain that part of the story. So this is mostly old material, in the sense old meaning like between 2010 and 2015, roughly. But it's continuing to develop in various directions I won't have time to talk about. So what I say will follow along the lines of some joint work that I did with David Agato and Greg Moore, also with Lotte Hollins. But for more recent related work, so I have joint work with Fei Yan, a paper with Alba Grassi and Chen-Yu Hao, which might be coming out either tonight or early next week on some specific examples of this story, which we investigate in great detail, related with David Dumas. And I also want to say that, of course, this is closely connected to many subjects in mathematics, and we learned a lot from exact WKB, from people working in cluster algebras, Higgs bundles, supersymmetric quantum field theory. So I've listed here kind of some of the references that are really the key ones for us. Is the work of these people, not mine. Okay, so let's get started. So I'm going to start out pretty concrete. So what's the data of the story? The data is a compact Riemann surface call it C. It might be CP1, an integer, n greater than or equal to 2. And so the story is going to have to do with WKB for nth order. So like for n equals 2, it would be a Schrodinger equation, and for higher n, it's some extension of a Schrodinger equation. And just as a remark, as a sort of guide for how to interpret the talk, most of what we say will be theorems for n equals 2 and conjectures for n greater than 2. So the geometric picture is going to be very, very parallel, but it's much harder to prove anything for higher n. Okay, so that's where we'll be. And then the last datum that we have will be a tuple phi, phi 2, phi 3, up to phi n, where phi I is a meromorphic section of the canonical bundle of the Riemann surface to the power I. So, what does that mean concretely? It means locally, how would you write it? You would write it phi I is, let's write pi. Pi of z dz to the I, with pi a meromorphic function. So if you're just thinking local coordinates, you should just think this is a bunch of functions. But if you want to think of terms under coordinate transformations, then you should remember that they're actually I differentials. So they transform with the ith power of the Jacobian of the change of variables. Okay, and then these are somehow the most important data, but then there are two more things that are kind of subleading in the story, but I should mention them to be complete. So one is that we take a spin structure on C. That's only for n even. And a complex projective structure on C, or let's say a CP1 structure. And what that means is that we're not going to treat every coordinate system on C exactly the same. So we choose a distinguished atlas of coordinate systems that are related to each other by Mobius transformations only. So for example, one thing you could do is just literally take C to be CP1, and then it has an obvious CP1 structure. But in general, we're going to equip C with the CP1 structure. So that's extra data. Every Riemann surface has one, but it has a bunch and you have to choose one. But that doesn't affect the leading order in this story. It kind of affects the subleading order. Okay, so that's the data that we use. And then given that data, you can write down a differential equation, kind of global version of a scalar ODE. So I won't write the construction, but I'll just say that these data determine an nth order differential operator, sometimes called an OPER, which I'll write D sub phi, which maps. Okay, and so it doesn't quite act on functions, but it acts on sections of, again, powers of the canonical bundle. Like this. So let's right away write the examples. So for this talk, I'm mostly going to focus on n equals 2 and n equals 3. So if n equals 2, and we choose a local coordinate patch. So we choose a local coordinate patch with coordinate z on our Riemann surface. Then once we choose that coordinate patch, we can trivialize all these bundles. And then the differential operator, now I'll write it just acting on functions, just becomes the operator. In other words, this is a kind of maybe you would work on the real. You would write like d squared by dx squared plus v of x minus e. This is this is a kind of version of that, where instead of having the coordinate x on the real line, we have the coordinate z on the Riemann surface. And v of x minus e will continue to this p of z. Okay, I think this is probably very familiar to participants in this particular workshop. And then let me just write the thing for n equals 3. So again, choose a local coordinate patch. And then what it looks like is, so now it's a third order equation involving two potentials now, P2 and P3. And the precise form of it, there's maybe one slightly unexpected thing, which is you have to write this derivative of P2. Okay, so there's a third order differential operator that you can consider. In a similar way, we write down nth order operators involving n, or I guess n minus 1 potentials. Okay, now, so we want to study these differential operators. Particularly, we want to study the solutions. In other words, the kernel of these differential operators. The size that are sent to 0 by these differential operators. And as you know, in order to do this, it turns out to be a good idea to introduce one more parameter. So slightly more generally, let's introduce the parameter h bar in C star. And then I'll define rescaling of my differentials just by, so phi 2 I rescale by h bar to the minus 2, phi 3 I rescale by h bar to the minus 3, and so on. And then I'll define my differential operator with an h bar to be just the operator with that rescaled version of the potential. So for example, when n equals 2, now this says I'm looking at the equation, I'm looking at the operator d by dz squared plus h bar to the minus 2, p2 of z. Okay, so that's the usual way h bar appears in the Schrodinger equation, in the WKB analysis of the Schrodinger equation. Okay, great. So okay, so now what we want to study is the solutions of the equation. So let's say the kernel of dh bar phi, right? In other words, the set of psi's for which d h bar phi psi equals 0. There's a rank n local system over the base C. Rank n local system over, well, to be exact, not over the whole C. So the equation has singularities, right? It has singularities wherever phi has poles. So we have no singularities away from those points. So C prime equals C minus the poles of phi. So here's our Riemann surface. Maybe we have some poles here. And then we have a rank n local system, which I'll call L. It depends on it's phi and h bar, but sometimes I'll just call it L. And L is just the set of solutions. So if I pick a given patch on my Riemann surface, then what L assigns to that patch is just the n-dimensional space of solutions of the equation over that patch. And then we have the continuation maps. You know, if I have overlapping patches, I get an isomorphism between the space of sections of one and the space of sections of the other. And so we have this local system, and in particular, if we continue the solutions around some path, what's the linear operator that I get? That's the kind of question you might want to answer. And okay, so we can use the exact WKB method to address that kind of question. So how does it work? all phi h bar. So to study it concretely, we want some ansatz which produces for us kind of concretely, well, we want to understand concretely the structure of this local system. And the key idea, the beautiful idea of how to do it is the WKB ansatz. And so to set up the WKB ansatz, let me introduce one more piece of, one more kind of strut, which is this ansatz is kind of best formulated. It's best formulated not on the surface itself, but on the so-called spectral curve. So let me introduce the spectral curve. So the spectral curve, I'll call it sigma. It really depends on phi, so I should write sigma phi if I'm being careful. And it's given by an equation, which is the following equation. So it's just determined by the data that we have, the Riemann surface and the potentials. You can write it like this: sum of phi I y to the n minus I equals 0. In other words, just a polynomial equation with the potentials as the coefficients, where we define phi 0 to be 1 and phi 1 to be 0, and then phi 2 up to phi n or whatever. So this equation, if you think about where it lives globally, where it naturally lives is inside the cotangent bundle of our Riemann surface C. And so, for example, so when n is 2, this is just the equation y squared plus phi 2 equals 0. In other words, it's a double cover. There's our surface C. Now I just draw it as a line. And then this surface, sigma, lying over C is the two solutions of this equation. In other words, it's the Riemann surface of the square root of minus phi 2. So it's a branch double cover with branching exactly at this locus, which I'll call delta, which in this case is just the zeros of phi 2, the zeros of the potential. In other words, the turning point, you would call terms in the context of the Schrodinger equation. And then when n is 3, we'll similarly have an equation y cubed plus phi 2y plus phi 3 equals 0. So that's some 3-to-1 covering. And the simplest situation is the situation where all the branching, so these kind of higher analogs of the turning points, in general, the branching could be kind of high location where all 3 sheets come together at one point, but let's assume that doesn't happen. So just to simplify our exposition a little bit, let's assume that we always have just simple ramification. And here, likewise, let's assume phi 2 has only simple zeros. Which is equivalent to the spectral curve should be smooth. Okay. So there's the spectral curve. And now we can formulate the kind of WKB ansatz for the solutions of our equation. WKB ansatz is like this. We write a solution of the equation, but it's only a formal series solution. So phi psi formal of z and h bar. We write it as the exponential of h bar inverse times an integral from some initial point to some final point of a one form, but the integral is taken not over the base curve, C, but over a path on the spectral curve. So the idea is, if you want to find the solution at some point, say If you want to find the solution at some point z, you're going to find it by doing an integral, but the integral is going to be over some path up here. You're going to choose one of the preimages. Well, the way I drew it, 3. This is n equals 3 case. In general, you're going to choose one of the preimages of your point, and you're going to do an integral from some other base point over here along some path like this. That's the ansatz for what the WKB solutions look like. And so, in fact, what I wrote here is not one solution; it's one solution for every choice of this point y lying over z. So here, y is a point in pi inverse of z. Let's call this projection map pi. So y is one of the preimages of z. And this lambda twiddle formal of h bar, well, that's some one form on the double cover, on the spectral cover, which comes to us as a formal power series in h bar. Yeah. I see now, I'm a little worried about my pedagogical choice here. So I omitted the motivation of this because I thought that we're in this workshop where everyone has probably seen this thing like 10 times. I hope that that's a simple assumption. If you have not seen this before, this is going to look a little out of nowhere. But let me suppose that you're at least broadly familiar with this formula. But I'll just remind you of its structure. So the shape that this thing has it's a sum of one forms, of a formal sum of terms, each of which is a one form on the spectral cover, where the first one, the initial term in the WKB ansatz, is the canonical Liouville one form on the cotangent bundle. So if you have, just because you have a curve that's sitting inside the cotangent bundle, it has this totally canonical one form on it. And the sort of naive, first approximation to a solution of your equation, you would get by literally just integrating that one form and nothing else. And if you do that, I mean, this is the exercise that you have to do. If you do that, you see that it solves the equation to leading order in h bar. And that's the whole reason why this thing kind of has a chance to work, is that there is a way of writing the leading order solution in this form. And then just by substituting, so then you say, okay, well, maybe I can make an exact solution by just extending the thing to a series bar. And that indeed works at the level of formal power series in h bar. So the lambda n here lambda n are determined recursively by plugging into the original ODE. Okay. And so for example, if n equals 2, this leads to a very concrete thing. It says that this lambda twiddle formal is the square root of minus p2 minus h bar p2 prime over 4p2. I'll just write one more term, plus h bar squared, square root of minus p2, 5p2 prime squared, or p2 double prime, divided by, what is it, 32 p2 cubed, etc. And so another way of understanding this, maybe what we should have said is, if you first just follow your nose, you write down this integral, and then you try to make sense of lambda twiddle formal, you just discover right away that you need to write the square root of minus p2, and so that this thing lives on the spectral cover, it lives on the Riemann surface where this lambda makes sense, is kind of dynamically determined for you by the equation. That's what tells you that you have to write the thing on the spectral curve. Okay, anyway, so this is the ansatz for writing down solutions of the equation. And then of course, the key difficulty with this ansatz, where all the interesting phenomena come from, is the fact that this series is in every example, the very most trivial example, this series is always it always has zero radius of convergence as in H bar. But this series is not convergent for any H bar not equal to 0. I'm saying there's no H bar not equal to 0 for which it's convergent. Okay, but nevertheless, the beautiful insight of the exact WKB method is that it's still possible to get something from it, and what you have to do is you have to do Borel summation. So you try Borel summation. And now there's an important statement, which is, I believe, still a conjecture for n greater than. I'll write it as a conjecture. Well, before even writing, yeah, let me first remind you of the Stokes graph. So the statement is that this works almost everywhere on C, everywhere away from the Stokes graph. Stokes graph is an object which is determined by the data of C and phi. So let me paste in some pictures of what a Stokes graph looks like. So again, I think that participants in this workshop have already seen a lot of Stokes graphs, I suspect, but I'll just paste in a couple examples to remind you. Can you see those all right? Okay, so these are a couple examples of the Stokes graphs in exact WKB. So this is the simplest one in the case of n equals 2 with the potential just equal to the function z. So this is the example of the ARA equation. This is a Stokes graph for the ARA function. This is an example of a polynomial potential in the plane. Again, for n equals 2, so just Schrodinger equation. Here's an example for, this is an example for n equals 3 of a higher order equation. And so here you see this phenomenon, the sort of signal new phenomenon in the higher rank equations is that the Stokes curves. So here, in this case, the Stokes curves were just emanating from the turning points. Here we have these higher order, the analog of a turning point in the higher rank case is a branch point of the spectral cover. And here you have trajectories which emanate from the spectral cover, which emanate from the branch points, but also when they collide, they can give birth to new trajectories. And so this is an example where you see that phenomenon happening here and here. And here's a slightly wilder example with n equals 4. All these examples are kind of, they're a little bit misleading in the sense that if I take a kind of generic example, the typical behavior is going to be that the Stokes graph is dense all over the surface. So here we're drawing very simple examples where the Stokes graph is not dense. The main exception to that is when n equals 2 and you have high enough order poles, then you can control it. But in general, the expectation is that unless you get lucky, things are probably going to be dense. Nevertheless, we can sort of start our life by studying the simple examples where it's not dense. So let's do that. Okay, and each path, each let's call them the wall, each wall of the Stokes graph, or Stokes curve, they sometimes call it, carries a label ij, where I and j are labeling two of the sheets of the spectral cover. So each of these paths should be labeled ij, and it's characterized by an equation. The equation is that along the path, the integral lambda I minus lambda j time multiplied by h bar inverse should be real. So each of these trajectories is a solution of some differential equation that's determined by the data of the lambda I, lambda j are the two sheets of the spectral curve. Yeah, so given the data of these phi and h bar, you draw the Stokes graph. Here are some examples of Stokes graphs, and then the conjecture is the big conjecture. Which I would love to know. I would love to know how to prove for higher n. Is that the series, the WKB series of y and h bar is actually Borel summable to an actual one form on the cover, lambda twiddle of y and h bar, except when y is lying on, well, except when y is lying over one of the walls of the Stokes graph. But we can say it even a little more precisely. Say when y lies on sheet, say sheet j, over a Stokes curve labeled ij. Okay. So now this, so that's a conjecture. It's a theorem in some case, a theorem when n equals 2. So the very important case of just Schrodinger equations. And phi 2 has at least one double pole. And some condition on the residue. So no residue m squared of phi 2 has argument of m equal to of h bar. So roughly speaking, when phi 2 has a high enough order pole and things are generic enough, then this Borel summability is actually known. So that's a theorem. So it comes from unpublished work by Kuike and Schäfke, which I learned about from a paper of Takei, but then also explained to me. But now there's a proof written out recently by Nikita Nikolaev. So one of the big questions that I actually wanted to ask, the exact WKB community is, what are the chances of proving this Borel summability more generally? But in any case, now let's suppose that Borel summability is true. Let's try to develop the picture a little bit. So assuming this conjecture is true, then so assuming this conjecture, then we have, so now our WKB ansatz, formerly just a formal series, now can be promoted to an actual form for those solutions, which I'll write exponential of h bar inverse integral from y to y naught, again, of lambda twiddle, now not a formal series, but an actual one form. So that ansatz gives us n solutions of the equation in any simply connected domain. Any domain U inside of our surface, the surface where the equation is, or more exactly, the surface minus the Stokes graph. Let me use W for the Stokes graph. And those solutions depend on the base point you choose. They depend on this y naught, but they depend on it only. Changing y naught only changes the solution by a scalar multiple. So up to scalar multiple, you're getting n distinct solutions of the equation, determined up to scalar multiple. And then, okay, there's a further conjecture, which is that they are linearly independent for every value of h bar. So let's also suppose that conjecture is true. Then you arrive at the following kind of geometric picture. We get a decomposition of the n-dimensional spaces into n one-dimensional spaces. Right, we have these n solutions that came to us by this procedure of writing the WKB ansatz and then doing the Borel summation. We have these n solutions determined up to scalar multiple. That's like saying you have an n-dimensional space which is decomposed into n distinct lines. Now, the ordering of those lines depends on some choice. So the really more geometrical way of saying it, is we have a picture like this. We have, we have our base curve downstairs, the spectral curve upstairs. And here we had the equation, which we formulated in terms of a local system, which we called L. L was this rank n local system. And what we're saying is that there's a corresponding local system upstairs of rank 1. And so here, if I look at, say, one of the stalks of this local system, it has, say, here that's a three-dimensional space, but it's coming to us decomposed as a direct sum of three one-dimensional spaces. And we think of those three one-dimensional spaces as being the fibers of a single local system, GL1 local system living on the cover. So, well, what is the local system on the cover? You can think of that local system on the cover as being the space of solutions of the equation d minus h bar inverse lambda twiddle psi is 0. I mean, the WKB ansatz is exactly engineered so that it solves this equation, this kind of so it solves this equation, and so so that's our rank 1 local system over the cover, which is kind of abelianizing the rank n local system downstairs. Now you say a little more. So suppose that the argument of h bar is generic enough. So everything I say, I think I'll just say in the most generic situation. Then there's actually a canonical way of patching. So far I did everything just away from the lines of this graph. But what's not obvious, but it's true, is that you can actually patch this local system upstairs, even across the lines of the Stokes graph. You can patch it across the Stokes graph to get a local system, let's say, rank 1 over the whole sigma, or more exactly, okay, there's a slight technicality. This thing has monodromy. To be a local system, it should have zero monodromy around any contractible loop. And this one, you know, as I guess the WKB experts will know, there's a monodromy -1 that shows up when you go around the branch points, the turning points in the case of the Schrodinger equation. So I'll call that an almost system. So it's not quite a flat GL1 connection over the cover. It has this little twisting. Call that an almost local system. But then in particular, so we have now this much simpler object on the cover, which is just a rank 1 local system. Then in particular, the natural thing to do when you have an object like that is to talk about what is its holonomy around a loop. So suppose I have a loop now in the homology of sigma. Yeah, I think I'll overlook this minus sign twisting now. So, so roughly speaking, if I have a loop just in the homology of the cover, now you define x gamma to be the holonomy of this GL1 local system over the cover. So that's now just a number, an element in C. And these are the, well, they've been called now by many names. So they, we could call them the Verreaux symbols. In the physics literature, they've been called the quantum periods or the spectral coordinates. Okay. So that's my kind of geometric viewpoint on how you think about these, how you think about the Verreaux symbols or the quantum periods. Is they really come from this process of taking a GLN thing and replacing it by a GL1 thing, which lives not on the original curve but on the spectral cover. Now, okay, so this a little bit to sort of other places in mathematics where this thing shows up. So in the end, what we've done is, or what we've described, you know, is a process where we started with this local system L over the base curve, and we replaced it with a local system over an abelian local system over the cover. That map, we described it, you know, in terms of WKB, and in particular in a kind of analytic way that involves this procedure of Borel summation. Now, one of the interesting things about it is that this same map from local systems downstairs to local systems upstairs had been studied before in completely other ways that had nothing. It's a purely topological thing. It has nothing analytic about it. So I want to briefly indicate that. So this map we can think of as coming from a map of moduli spaces, or let's say, well, yeah, it corresponds to a map of moduli spaces, spaces of flat connections or local systems. So we have, on the one hand, a moduli space of GLN flat connections over the base curve, and on the other hand, we have a moduli space of almost flat GL1 connections over the cover. So I'll call this map ab phi h bar. So for every phi in H bar, we draw the corresponding Stokes curve, the corresponding Stokes graph, and just from that Stokes graph, and then essentially some elaborate linear algebra, but without talking about Borel summation, you can write down a map from the moduli of GLN connections downstairs to GL1 connections upstairs. Now, the virtue of that, well, one virtue of that is that this space is a much simpler space than this one. This one, if you wanted to just describe abstractly what's the space of all flat connections, well, you can say it's like moduli of representations of the fundamental group or something like that. That's a relatively complicated space. Here, on the other hand, this space is just literally C star to some power. It's literally just parameterized by the holonomies, what we were calling, the Verose symbols. Those are literally just coordinates, the most obvious coordinates on the moduli of GL1 connections. So if you have a map from one to another, in fact, this map turns out to be a local diffeomorphism and in fact local symplectomorphism. So these two spaces in particular have the same dimension. So what this map gives you is not quite global coordinates, but local coordinate systems. Local coordinate systems on M of C GLN. And those coordinate systems, you could just independently of anything about exact WKB, you could ask, well, what are those coordinate systems? And it turns out that in the simple enough cases where we can understand them, they're very well known and important coordinate systems. So, so in simple cases, these recover coordinates that had been studied before. So for example, so again, in the one case where everything is proved, the case of n equals 2, phi 2 with poles, at least one pole of order greater than or equal to 2, an H bar is sufficiently. In that case, the quantum periods turn out to be the so-called Fock-Goncharov coordinates. Or complexified shear coordinates. On the moduli of GL2 connections. And similarly, if n is greater than 2, and we choose all the higher differentials, phi 3 up to phi n, to be much smaller in norm than phi 2, and again, phi 2 with poles of order greater than or equal to 2, then again, so then we're studying the moduli space of these higher rank connections. It's a much more complicated space. Nevertheless, people had discovered some very nice coordinate systems called the cluster coordinates or the Fock-Goncharov coordinates in higher rank. And once again, you recover exactly those coordinates by this exact WKB procedure. Okay, if you're not a cluster enthusiast, then this may not resonate with you today. But one day, if you encounter someone who's interested in cluster algebras or cluster coordinates, you can know that secretly what they're talking about. So they will tell you some unbelievable construction of what the coordinates are. It sounds very complicated, but you just have to know that it's exactly the same thing as taking quantum periods. So for me, this was like a happy explanation of why the cluster coordinates. One way of understanding why the cluster coordinates are actually important is because they are the ones that come from exact WKB. You also get, by the way, other, maybe I'll just mention, there's the other kind of famous coordinate system that people like to use on moduli spaces of flat connections for SL2 is Fenchel-Nielsen coordinates, and those also show up in this story. They show up when the Stokes graph contains a closed loop. So roughly speaking, you get the Fock-Goncharov in the most generic situation where you don't have any closed loops or any saddles or anything. If you have a saddle, then you get some slight variant of the Fock-Goncharov. If you have a closed loop, then you get these Fenchel-Nielsen coordinates. Okay. So I see I'm almost out of time, but maybe I have enough time to say at least a few words about this, the Stokes automorphisms. Okay, so our situation now, let's talk about Stokes automorphisms. Our situation now is I've formulated exact WKB as a way of constructing kind of coordinate systems on the moduli space of flat connections. So we've described for each h bar and phi some local coordinates on the moduli of flat GLN connections. And this local coordinate, I told you that certainly didn't prove to you, that depends only on the topology of the Stokes graph. Say W of theta and phi. Sorry, W of h bar and phi. And so the picture that we have then, if I draw a very schematic picture of the parameter space, we have, as we vary the potentials in our equation and as we vary the phase of h bar, we have this situation where the parameter space is kind of divided chambers. Each chamber is a region where the topology of the Stokes graph doesn't change when you move in that chamber. And then there are going to be some walls where when you approach the wall, the topology of the Stokes graph suddenly changes. And maybe the picture of the chamber structure, looks something like this. So some complicated chamber structure. So we have walls where the topology of the Stokes graph changes. And so since we have two coordinate systems, so when we approach a wall, we have, from the two sides, we have two different coordinate systems. And so we can ask, what's the transformation of coordinates that relates one coordinate system to the other? So each wall has attached a coordinate transformation, which I'll call A sub W. And you can think of it as being a map. The most canonical way of describing it is to say that it's a map from the abelian connections to themselves. So it's an automorphism of the moduli of abelian connections. In practical terms, remember, this was C star at the end. So in practical terms, it's an automorphism of a torus. And what are those automorphisms? Let me just show you a couple of pictures and then say the thing about the kind of main conjecture in physics about these automorphisms, I guess. And then I'll finish. So the simplest example, which I think will be very familiar, in the case of n equals 2, you have a picture like this. So this is a picture of how the Stokes graph varies as I change the, so here I'm writing theta as the argument of h bar. One of the ways that the topology of the Stokes graph can suddenly change is that so for generic values of this phase, the Stokes curve never runs from one turning point to another, but there's special phases where you do get a Stokes curve running from one turning point to another. That's an example of one of these walls. And at the wall, the transformation of coordinates that you get turns out to be the following. So I'll call it K gamma. And so it maps the coordinate x mu to x mu times 1 minus x gamma to some power, and that power is the intersection pairing. It's controlled by the intersection pairing between gamma and mu. So that one I think is probably very familiar. Anyway, if it's not, so there it is. So it's some simple concrete formula for the change of coordinates from one domain to another. In the cluster world, these are called cluster transformations. And the fact that they're so simple is somehow one of the key things in the cluster, in the story of cluster coordinates. So they really like the fact that you have a whole bunch of local coordinate systems that are all related by very simple concrete transformations of this kind. Now, let me show you an example for n equals 3. So here's again a way that the Stokes graph can change its topology. So now it's a little more complicated. If you look at the left and the right, you can see, I hope, how the topology has changes. These extra legs are going down in a different way on the left, right. And in this case, if you look at what's happening at the moment when the topology changes, the object that appears is not, it's a new kind of object. It's this kind of three-stringed web here. But once again, the automorphism turns out to be exactly the same. The Stokes automorphism turns out to be of exactly the same form. So from the point of view of the Stokes automorphisms, you can't really distinguish these saddle connections, this simple object here, and these trees that appear in the higher rank situation. However, for n bigger than 2, so I just drew for you the simplest situation, but unfortunately, or fortunately, so many other topologies. Okay, I see I have 1 minute. I think I'll finish in 1 minute. So, you know, the general topology of the kind of new object that could appear somewhere in the Stokes graph, it can have, you know, maybe 2 legs like this, that join like this, but then something comes off here and has a little loop, and then here there's another loop, and then it goes like that. You can have objects of arbitrarily complicated topology, whereas in the case n equals 2 that we're most used to, the only thing you can have are these saddle connections and closed loops. So for n equals 2, the other possibility is a closed loop, which gives you the automorphism k gamma to the minus 2. In higher n, you can have unbelievable proliferation of topologies, but now here's the statement from physics. So the conjecture from physics or DT theory is that the automorphism at a wall is always of the form, it's a product over cycles gamma, homology cycles gamma, of these automorphisms. So this particular automorphism that I wrote before, k gamma, I wrote it here. It's just that particular automorphism occurring to some power So above, I showed you an example where the power was 1. I told you that for a closed loop, the power is -2. The conjecture is that you can always factorize it like this, where the numbers that appear here are always integers. And we have an algorithm for computing these numbers for any particular topology, but that algorithm, I think, doesn't show that they're integers. So the integrality really comes from the fact that these are the dimensions of Hilbert spaces of particles in a certain supersymmetric quantum field theory. And leave myself time, obviously, to say much about that, but maybe that's fine because that's somehow not a mathematically rigorous statement anyway. Maybe the best thing I should say is just that these integers, there are these numbers which appear in the Stokes automorphism. They're conjectured to be integers, and moreover, they should be understood as the dimension of some Hilbert space. It'd be very interesting to identify that Hilbert space in some intrinsic way, kind of just in the language of exact WKB. Okay, sorry that I went a little over time. I think I better stop now. Thanks a lot.
So thank you very much for this really beautiful talk. So any questions from anyone?
Am I allowed to ask a question?
Oh yeah, absolutely.
So my question is, so there's many things that that I don't know that I think might be known in the exact WKB literature. And one example of a concrete thing is, I would like to know whether this object appeared somewhere. I know that there's some literature about these higher rank Stokes graphs, and I'm wondering whether someone calculated this this Stokes automorphism. I can well believe that that's somewhere in the literature, and in that case, I should be citing it, but I want to know where it is. Okay, that's my question. So if anyone knows, please let me know.
Anyone? No, I don't know, but so I have a couple of questions. So you mentioned for, I think, n larger than 2, the generic cases, the Stokes graph would be dense, right?
I think so, yeah.
So is anything known about what happens in that case?
I don't think so. This is another place where I think it would be really great to have some, in the case n equals 2, there's this whole book by Strebel called Quadratic Differentials, which is just all about the trajectories of quadratic differentials. It tells you everything you want to know about the global behavior of the Stokes graph, on these compact Riemann surfaces. That book does not exist for this, for the higher n situation. I'm guessing it's going to be typically dense just because, even for the quadratic differentials, it's dense if you don't have the poles. And somehow in higher rank, the poles don't help you as much as they did for n equals 2, because you can have this phenomenon where, 2 trajectories give birth to another one, and then that one runs into someone else and gives birth to another one, and that one runs into someone else and gives birth to another one. And in that way, they can kind of avoid being attracted to the poles. They can just constantly be generating new ones. So yeah, I mean, I made some conjectures about which cases are finite and which cases are infinite, but in short, the conjecture says that most cases are infinite. But it would be great to prove anything about that. I mean, I think it's a very wide open. My impression is it's pretty open.
Yeah, that's very interesting. So anyone? What we think?
Can I ask a question? From your point of view, do you think it's really important that the WKB ansatz is that we have this analytic version of the WKB ansatz in the complement of the walls, or is it more that we use it to access Voros symbols, and it's somehow, if we had a different way to access Voros symbols, then somehow you know, all these statements that you mentioned about Stokes automorphisms, we would have them.
Well, right. So as far as the Stokes automorphisms go, that's right. The Stokes automorphism is a totally topological thing, and as far as that part goes, those integers and everything, you do not need the Yeah, that's actually an important point. You don't need the exact WKB machine for producing the abelianization, as long as you have some way of producing it. That's enough to talk about.
But even
having
the WKB picture in mind. So, for instance, the last thing that you mentioned, which I thought was fascinating about trying to identify these Hilbert spaces, that somehow has intrinsic relation with some sort of WKB picture. But I'm just wondering if it's really necessary to have access to analytic WKB ansatz, or is that really a stepping stone?
I mean, I think it depends which application you want. So, I mean, one of the applications of this stuff, I mean, as I think people know, one of the applications would be, suppose you wanted to study like the trace of the holonomy around some loop, like just as a benchmark for the kind of thing you might want to know about your original equation. Suppose you want to know the trace of the holonomy. Sorry, the holonomy around some loop of L. If all you know is the kind of topological story, then what you get is the following fact. You get the fact that this is expanded as a sum of Verroes symbols, right? Multiplied by some integers. If you don't know anything about the kind of analytic behavior of the Verroes symbol, then it doesn't tell you that much, right? It tells you it's expanded in terms of some other things, and maybe these things are somehow, you know, slightly nicer looking objects. But what you want to know in that case, right, is, for example, that the X gamma has an asymptotic series expansion that starts with, you know, the period divided by H bar. And so for that kind of stuff, I think you need to have gotten them in this specific way in order to show that they have the asymptotic expansion that they're supposed to have. I don't know how to get it.
That's the reason I'm asking the question, because I don't think so. I think you can get them in a simpler way.
Oh, you think I'm wrong? Okay. I would be interested to hear about that.
I mean, basically, like the most straightforward way to get this property that you wrote down is indeed if you write down all your WKB ansatz in higher rank, and they're all, you know, somehow you had a statement that says that there is you can Borel resum them, or whatever the machinery may be.
Right.
And then the Verroes symbols are certain ratios, basically, of these expressions. And then and then you get this statement. But the first step in that argument seems very hard, as we know very well. But I think the second statement is actually possible to get by different means.
You think you can get the asymptotics without all that stuff?
Yes.
Okay, I would be interested. Yeah. I would be interested to see that. I didn't know that. Well, I mean, in some cases, I guess. Okay, I think, you know, in rank 2, it's true you didn't need the Borel summation, but you did need some analysis of the differential equation. I mean, of course, couldn't get it completely for nothing.
Of course.
Yeah. No, that's true. Maybe you can get it without the whole Borel summation. No, I agree with that. Certainly, for n equals 2, that's a true fact. So maybe, but I don't know. Now this Borel summation seems so nice to me. It feels like that's the morally correct.
But somehow I'm not even saying that to get rid of the Borel summation. I actually, for this statement, I would still use Borel summation. It's just it's a Borel summation of a much simpler object, just on a different curve. Yeah. So you have to do a little bit of a geometric trick to get basically a quadratic differential, but not on your original Riemann surface, but on some auxiliary surface, which comes to you canonically through this geometric construction.
I see.
And then, and basically the explanation here is that when you do this, this abelian local system that you construct on the spectral curve, it's not exactly that the kind of, you know, sections of that abelian local systems are sections of your original rank n system. They're certain, well, from my point of view, they're certain, they're related to the associated graded of certain filtrations on your original local rank n local system. So it's not there's
you
not
you have a different point of view from me on
yes,
this, yeah.
yes, but you see, that's the reason I'm saying this is because when you take that point of view, then the thing that you can resum is it's not really a section of your original bundle, it's just related to a section of your original bundle. But the Voros symbols are expressed in terms of this kind of slightly more abstract object, if you like. And then, so because you have access to these objects, which are not sections of your original bundle, you use them to build the Voros symbols, and so basically that's that's the very rough idea of an argument to avoid basically constructing the WKB basis, analytic WKB basis. So that's hard.
All right. I think this is beyond what we can discuss in the question time.
Yes. Yeah.
It sounds interesting. Yeah, I should say, of course, the point of view I've described, Nikita, I should also reference some of Nikita's papers, because Nikita has developed a lot of this theory in a much more rigorous way than in the physics papers that I mentioned at the beginning.
Any more questions? Oh, I might ask another one. So when I was learning all this cyberwritten theories and so on, not even the concept, just classical level. I was reading different sources and so on, and they all have, not all of them, but you can have different cyberwritten curves for the same theory. The statement is that, they're all physically equivalent and so on and so forth. But if you think about the quantization procedure, it's not obvious to me that those different curves quantized would lead to the same structure. But
right.
At the same time, if there's this very nice relation between these holonomies and the Hilbert spaces of the underlying theory, there has to be some connection, I suppose, between.
But here, I'm not so sure about that. So I mean, here in the story of this Schrodinger equation, or this higher rank equation, it really involves two ingredients. So it involves, I would say, a 4D n = 2 supersymmetric field theory, and that's the thing that has a Seiberg-Witten has many Seiberg-Witten curves, right? But then, in addition, it involves a two-dimensional surface defect in that theory. And once you fix this additional data of a surface defect, that really picks a particular Seiberg curve in a particular, way of representing it as a cover of a surface. And so I think it's really these two things together that produce for you the OPER. Now, then there's the question of why is it that sometimes, I mean, it is still true that for some reason the periods of different surface defects are related. That's a true fact. I think even their quantum periods are related, and you can ask, why is that? Yeah, we kind of understand that by putting the n = 2 theory in omega background. Well, let me say it like this. There's some restricted class of Seiberg-Witten curves that you can get if you say, I'm not just taking a 4D n = 2 theory, the 4D n = 2 theory with a surface defect. And I'm going to use that surface defect to produce for me the Seiberg-Witten curve. Each one of those is going to produce for you some differential equation, like the kind of thing we're studying here. For each one of those, you could ask, now, what are the quantum periods? Then there is a funny fact that the quantum periods for different surface defects come out to be the same. And you can ask, what was the reason for that? I think the reason for that is that, you can also describe them in terms of the original n = 2 theory just placed in omega background. Yeah, but I don't think this has been completely spelled out in a real clear way, actually. I think you're right that there's a little puzzle.
Yeah, from the differential equation perspective, it's kind of non-trivial to have these relations between different
No, I agree. I agree. Yeah.
Okay. So any more questions? So if not, I'll stop the recording. And thanks again, Andy. I'll pass in
Thanks.
on behalf of everyone for this beautiful talk.